Hi guys. All right, so we're going to go through some integrated rate law notes. I'm sorry if I sound a little bit distant while I'm doing this. I'm kind of moving around, and it is a new laptop as well, so hopefully the sound and everything is coming through all right. So we'll try to get through this fairly quickly. I'll try to keep it short and to the point, and so let's just get going. Okay. So before we really start talking about integrated, you can see that this is a problem we've used as a warm-up in the past. So this is just showing a differential problem just as an example. So this is still differential rate law. And in differential rate law, we have these 4 different experiments. We can use the values from different experiments to figure out how each compound or each reactant is affecting the rate. So like we can look at iodide right here. It's doubling while the other 2 are staying relatively, well, not relatively, they're staying the same concentration. So we can see that this is going up by 2, or this is going, and then so is the rate. The rate is also doubling. So we know that this guy is first order. We can do the same thing with the other reactants. So if we look, let's see, I actually have to look at this now. If we look at experiment 1 and 4, this is going to double. And the other 2 are staying the same concentration. If we see here that this is getting cut in half, so because our hydroxide is doubling, but it is causing the rate to get cut in half, this guy is going to be to the first order, or to the negative first order. And then last but not least, our hypochlorite here, we can look at experiment 1 and 3. So the other 2 are being held constant. Here again, we're getting that double, so it's going up by 2. Here it's being doubled, so first order. So our iodide is to the first order. Our hypochlorite is to the first order, and then hydroxide is to the negative first order, because when it doubles, the rate is cut in half. So the rate law for this is just that rate is going to equal K times all of this. So that's how we would figure it out for differential. So that's our baseline example. So the rest of this should look at things in terms of integrated. So if this was our rate before, we can figure out order for everything. So the value on K. Overall order is just adding up all of these. So 1 plus 1 plus negative 1. These guys cancel each other. So our overall order is first. Since it's an overall order, the overall order is first, units on K are going to be seconds to the negative first. The way that I can figure that out, so we have rate times K times this, this, and this. So the units on rate are going to be concentration over seconds. So I know that's what all of these 4 factors multiplied together unit-wise have to combine to make. So I'm trying to figure out what K would be. So K is my question mark. I know what the units on everything else is. So iodide's units are concentration, so that's molarity. Our hypochlorite is also molarity. And then because hydroxide is the negative first there, it's going to be molarity to the negative first. So I have molarity to the negative first, and molarity. So essentially, this molarity and this molarity of the negative first are going to cancel each other. So I know that K, the unit on K times this this molarity on iodide should equal molarity over seconds. So that simply just means that K is seconds to the negative first, or that's the same thing as saying 1 over seconds. Those two together, so this and this, will get me that unit. So we'll talk some more about like how I figure out those units kind of stuff in a second here. So what happens when reactant concentration doesn't stay the same? So this is still differential. So determining the rate law for something where we only get one reactant that stays the same in this whole thing. So first off, we'll use the experiment 1, 2 where things do actually stay the same. So right here, this whole thing is increasing by 1.5. So for S2O8, it is changing by 1.5. And our rate is also changing by 1.5, and you can kind of, I calculated that out ahead of time, so I already know it. So essentially, this is what I'm looking for. I know that 1.5 to the power of x is equal to 1.5, so x here has to be 1. So that means that this guy is first order. So since I know he's first order, I can't isolate him to be the same because there's no experiment where he stays the same. So I can just kind of pick a random experiment. I'm going to pick one that works out a little bit easier for me. So I'm going to pick 1 and 3. So if I look at 1 and 3, I know that S2O8 is doubling. So this is going up by 2. And our iodide friend here is increasing by 1.5. And then the overall is changing by 3. So what I know is that S2O8, which I already know is first order, when it doubles, and I already know it's first order, when that changes, times the 1.5 change from iodide to the power of x, I should get my rate to triple. So I can kind of just use that to figure out what x is. Well, 2 times 1.5 does equal 3. So that means that x in this case is 1 as well. So that means that both of them are to the first order. So this guy's to the first order and this guy's to the first order. That looks a little bit more complicated. I'm sure we'll do some practice with something like that in class at some point. So just kind of keep that in mind. Okay. So going back to talking about units of K. So units for K, the rate constant, change based off of what the overall order is. So you can always figure out what the units are by canceling out things. So that's what I did earlier. So if I look at this example here, I know, again, that I need to have rate equaling having units of molarity per second. I have molarity times molarity here, molarity squared, and molarity to the first. So I can kind of look at all of that. So I can kind of look at all that, and I know that I need to cancel this guy out. So that means that K in some way needs to cancel out this molarity squared. I can keep this because that is going to carry over to what I want. And then I still need a 1 over seconds thing. So that means that K here would have to equal molarity to the negative seconds times second to the negative first. So that would cancel out with the molarity squared. I would have the seconds to the negative first, which is what I have here. and then I have my molarity. So that's how I can figure it out by cancellation. The other way you can figure it out is if you just know the overall order, the units are always the same on K. So first order, the units on K should be seconds to the negative first. Second order, it's going to be molarity to the negative first, seconds to the negative first. And then if it's third order, like the last problem, it's molarity to the negative second, seconds to the negative first. The one thing this doesn't cover is zero order, which you'll start to see coming up a bit more frequently. Well, if you look at the transition here, we went from seconds to the negative first to molarity to the negative first, seconds to the negative first, to molarity to the negative second, and seconds to the negative first. So if we go the other way, to zero order, it is simply just molarity per second, or molarity times seconds to the negative first. So if you remember that first order is seconds to the negative first, and just remember sort of what the transition is each direction, you can kind of figure it out. So this is going to be really helpful with integrated, which is why we're covering all of this. I know this seems like we're 10 minutes in and I haven't covered any integrated. I'm sorry, I'm getting there. Okay. This problem right here is just kind of another one of those fun little rate things. It's another differential problem, so you guys can look at it if you want to use it. It's another practice chance too to figure out what the overall order is and then what the units for K is. I'll pause it really quick and then I'll show you everything so you'll see it appear in about 3, 2. Okay, and through editing magic, there's everything. So C2H4 is the first order, O3 is to the first order. That means the rate is equal to K times C2H4 to the first order, O3 to the first order. So overall it's second order, which is why I know what the unit is, and then I can solve for K. Sweet. Manipulating the value of K. So there's a couple different ways that you can change the value of K. Changing concentration is not one of them. So changing concentration doesn't change K in any way. K is a constant for that. It will change the rate, but not the value of K. Whereas the value of K will change with temperatures. So K will equal one thing at 273 Kelvin, and you'll have a different K, like K2, at like 773 Kelvin. So different temperatures have a different K value, and then catalysts are a completely different mechanism, so they have a completely different K. So when we talk about catalysts and mechanisms, like you'll see why they have a different K later on. All right, here's where we get to integrated rate law. So differential is looking at instantaneous rates and using that data to solve for K and different things at instantaneous moments. Integrated rate law involves time. It is looking at things over time. So we're looking at the entire progression of something over time and using that to figure out order as well as K and all that other kind of stuff. So whenever we look at integrated, we only generally look at one reactant at a time, and we look at a graph of that reactant versus time. So that's the general idea for integrated. Then what we want to try to do is we want to try to get that to be a straight line. So we can figure out what order this reactant is based off of which type of graph will give us a linear trend. So this trend you can see right now is not linear, so this graph doesn't give us the order that we want, so we would have to change the graph style to give us a linear graph. Here's what I mean by that. So you can see 3 different graphs here. It's all for the same data. The only difference here is we have concentration versus time, natural log of concentration versus time, and then 1 over concentration versus time. So depending on which of these graphs are linear is going to tell us what order it is. If it was the concentration versus time, it would be zero order. But you can see this graph is not linear, so this particular set of data is not zero order. In the natural log of A versus time, if it's linear, it's first order. Well, you can see we have linear data here, so this is definitely first order. But just to kind of go through everything, if it was the 1 over concentration versus time, it would give us second order. So basically how we plot this graph is going to tell us what order it is. We would plot it all three different ways. Whichever graph is the most linear gives us the order of that reactant. So from there, we also have the integrated rate law and half-life equation that goes with it. Since this data is first order, that means that this is the correct rate law to use for A. For whatever compound A is, it would be the natural log of the concentration of A is equal to negative KT plus natural log of A naught, or natural log of concentration of A naught. Our half-life for that equation is T1/2 is equal to 0.693 over K. This is also the natural log of 2 over K. Your book will probably go through a whole explanation of where that comes from and skip the important part. But in general, whichever order it is tells us, don't need to go back that far, tells us which equation to use. Now, some important things to notice here. Zero order, it is negative KT. First order, it is negative KT as your slope for this graph. Second order, it is positive KT. So zero order and first order will both have a negative slope, whereas second order has a positive slope. So that's one of the important things to remember when you're trying to remember which equation you want to use and like how to set everything up. Second order has the positive slope. The other two are negative slopes. You also can notice that in the half-life equation, for zero order and for second order, concentration, the initial concentration is part of that equation. For first order, there is no initial concentration. It doesn't matter what it is. And that's actually a really key important thing for the half-life of first order. But we'll kind of get into some practice for this whole thing. So again, we're still only focusing on one reactant. But let's look at this. So over here, this is concentration versus time. So this is zero order. Since I see that the graph right here is concentration versus time, automatically I know that this is zero order. And so in this case, whatever red is as a compound, actually since it's red, let's make it red. Red is going to be to the zero order, whatever red is. If we look at the next one, well, we have natural log, so this is first order. And so that means that green, whatever green is to the first order. And then if we look over here, this is our second order graph because it's 1 over concentration. So the blue line, which whatever blue is representing, is to the second order as far as this reactant goes. So decomposition of an unknown molecule, A was found to be first order. So we know that this is a first order process. So we have this graph below. We don't have a labeled axis. Well, because it's first order, we already know that this label, since it's linear, has to be natural log of A. So this is just a lot of practice of getting you guys used to knowing that if you see a natural log of A graph and it's linear, that's first order, et cetera, et cetera. Because this is first order, the units on K, well, we know that this is a first order. So because that means that the units on K have to be seconds to the negative first. That's where that little table a couple slides ago comes in handy. If you just remember what it is for each order, then you know what the units on K is. All right, so this problem, we have a couple different things to look at. So we have ethanol, 1 over ethanol, natural log of ethanol. So 0, second order, ooh, we changed the order on you guys a little bit, and first. So there's our first order. Our linear guy is this one. So he is 0 order. That means that this reactant is 0 order, which means that he doesn't really affect the rate at all. So determine the order of the reactant. We just did that, 0 order. Write the rate law for this reaction. So there was that slide, there's a few slides ago. If we go back, boom, there's all of our integrated rates. This is for 0, so this is the one that we want. So it is concentration of AT is equal to negative KT plus concentration of an initial concentration of A. So if we go back to the slide that we were on, I'm just repeating that entire thing. Well, now we have ethanol. So that means concentration of ethanol, ETOH is the shorthand for that, with respect to time is equal to negative KT plus our initial concentration of ethanol. How to figure out the initial concentration? Well, in this case, it's our y-intercept. That's our initial concentration. If we were talking about a second order, well, we would already know what the y-intercept was for second order. It would be 100, and right here it would be about negative 4.6 or so. So we can look at those y-intercept points, just know what they're replacing. If it was second order, this right here, or sorry, if it was first order, this right here, the y-intercept would already be the natural log of the initial concentration, so it would replace this entire thing. If we took the y-intercept for second order, it would replace this entire thing, not just the A naught part, but the 1 over A naught as well. So that's kind of important to remember. Determine the rate constant for this reaction, including units. So now we just solve for K. To do that, pick a random point. So in general, I want to pick a point that's easy to use. I'm going to go with that one because it's kind of right on the dot for everything. So that's what we'll pick. So I can just plug in values now since I know what everything is. So I know that at that time, our concentration of ethanol is 0.006 molar. I know that we have negative K, so K is what we're solving for. Our time at this point is 1,000 seconds. And then our initial concentration of this guy is 0.01 molar. So I can now solve for K. K is equal to 0.006 minus 0.01 all over 1,000. I should preface that. I should say negative K. Important keynote there. Negative K is equal to all this, so that's negative 0.004 over 1,000. So that means negative K is equal to negative 4 times 10 to the negative 6th. In other words, K is equal to 4 times 10 to the negative 6th. And because it's 0 order, the units are molarity per second. Boom. Done. All right. Next example. So we have C5H6. This guy is reacting with itself to form C10H12 according to the process. It gives us the graphs of all of this. The data was collected during the experiment, so over time. So it wants to know what is the order of the overall reaction, what is the rate law for the overall reaction, calculate the rate law, so K, or the rate constant K for the reaction with units, and then calculate the concentration. So I want you guys to pause this video, try it out yourselves, see if you can solve A, B, C, and D, and then I'll show you guys the answer. So I'll give you guys a 5-second countdown. Please pause before that. So 5, 4, 3, 2, 1. And with the magic of editing, there's all of our fun answers. So let's zoom in and look at this a little bit. First thing, what is the order for the overall thing? Well, I know the order for the overall thing simply based off of that, since it's concentration in the first, which is the same thing as saying 1 over concentration. That has to be second order. So second order. So I just use the second order equation, which is 1 over the concentration at time is equal to KT plus 1 over the initial concentration. Remember here that it is plus KT, so positive KT here. How did I find the initial concentration? Well, I could have used this intercept here, which would replace that entire fraction, but it's kind of hard to tell where that point lands between 25 and 20. It's not the most precise, whereas this right here is much easier to use. So that is the initial concentration because this is the concentration versus time graph. So I can use that, plug that in for my initial concentration of 0.04 because it's a little bit more precise than the other graph. So there's my initial intercept concentration. I can now pick a time. So I chose 90 seconds simply because it seemed to be a bit easier to read. I'm still kind of estimating a number a little bit, like it's not perfect, but it's somewhere about 40. So 40 is equal to K times 90 plus our initial 1 over our initial concentration. K is equal to 0.167, and then since it's second order, that's molarity to the negative first, seconds to the negative first. Last thing is it says, what is the calculate the concentration when 250 seconds have passed. So now that I know what K is, I can solve for the concentration at a particular time. I just take K times the time it wants plus, again, our 1 over initial concentration, plug and chug, and we get 0.015 molar. All right. So last thing, one of the last things to look at here is half-life. So as we talked about in one of those earlier slides, let's see if I can find it really quickly. This one, each order has its own half-life equation, and that's simply because of the behavior of half-life. So half-life is talking about how long does it take for you to lose half of the material you're talking about. In this case, half of the concentration. So the half-life equation, amount of time it takes for half of the reactant to decay by, is going to be dependent on what order that reactant is. So if we are talking about concentration versus time, so 0 order. For 0 order reactions, the half-life time is going to get smaller and smaller as the reaction goes on. So the more material you start with, the longer it will take for you to get to that first half-life. Second half-life will be shorter, so you'll get to it faster. Third half-life will be even shorter, so you'll get to it even faster. So this process, you cut your material in half at an accelerated rate. In first order reactions, the half-life is consistent. It is always the same frame of time. This happens a lot with nuclear Reactions, so nuclear reactions, nuclear decay. Yeah, if I spell things correctly. Nuclear decay is by definition a first order process. So if you guys remember back to nuclear decay, you'll remember that it always decays at the same rate. That's because it's a first order process. Half-life is independent of concentration, so it's always going to be the same half-life no matter if you're starting with 0.2 or 0.1 or 0.05 molar. It's independent, which is why there is no initial concentration in that equation. And then for second order, you can see that the half-life time increases, so it gets longer and longer. It takes longer and longer for you to lose half that material. So it slows down. The process essentially slows down. The big one to remember is first order. That's the one they like to bug you with a lot. In general, you know if they ask you a half-life equation, which one it is, because on their little cheat sheet, they generally only give you one of those equations. So whichever half-life equation they give you on the cheat sheet is probably the one they're going to ask about. Generally, it's first order. So one more time, just so you see everything. Here is the zero order equation with, so zero order, that's the rate order equation, that's the half-life equation. First order, same thing. Second order, same thing. So you see them all together. You should know all of those rate equations pretty much off the top of your head. So you should know zero order is concentration equals negative kT plus initial concentration. First order is natural log with negative kT. Second order is 1 over AT with equaling plus positive kT. You don't need to memorize all of the half order or half-life ones, but I would say that this guy, our first order one, is probably a good one to know. So just knowing that is 0.693 over K, it's pretty easy to remember. And it's an easy one to deal with. Decomposition of hydrogen peroxide. So I do want you guys to try to look at this one. I know I'm like chewing up a lot of time here, but I want you guys to try to figure this one out. Notice I don't give you any graphs because you guys can graph this yourselves. You have a nice graphing calculator. I'm going to tell you how to do this. So to use your graphing calculator to figure out what order this whole thing is. Well, you have list functions, so you just need to make that list 1. You make this list 2. So you have list 1 as your time, list 2 as your concentrations. In class, we will probably show you, if we can, how to do this, but list 3 and list 4 you'll leave blank to begin with. Get list 1 and list 2 in there, and when you're working, you can go up to the top where it says list 3 and tell the calculator that list 3 is equal to something along the lines of like 1 over list 2. Well, that gives you your second order graph line. And you can say that list 4 is equal to the natural log of list 2. So now that you have that, it will graph all 3 lines at the exact same time for you. You just need to look at which line is linear, so which data set is giving you a linear trend, and you know what order it is. So try it out with this problem, see if you can't do it, and we'll kind of talk about this in class. For this one, as you're doing everything, it should be first order. The way to double check that is you want to look at what the R squared value is for all those lines. So R squared for this line is 0.9997. Whichever R squared value is closer to 1, whichever R squared value is closer to 1 is going to be your most linear line, and so your first order is the most linear because it's the closest R squared value to 1. Last but not least, this is pretty much what I just did. So on the inspired, Here's how you do it. If you are doing it with a normal like TI-84 or whatever, you can also do the same thing, but in general, you put all 4 of those data columns in, like I just talked about. Here, if it's inspired, you can use the test, so menu stats, blah, blah, blah. For TI-84s, you just click on stats test, and then you want to do a linear regression t-test, and then you just look for that r-squared value. So we'll do some more of this in class, hopefully give you guys some practice with this. But it's a nice, fun little feature, and it's really helpful because they like to throw you one of these kind of questions on the exam and have you graph it quickly, so this is a quick way to do that. Thank you guys for putting up with me for 35 minutes. Hope isn't too bad. Please come with questions if you have them, especially with this calculator stuff or like what was Charvella talking about. And I hope you guys have a wonderful rest of your day.